models, derived models, or potential flow kind of models. Uh, any other specific part that you heard, like any experimental task that you want very interested on so far in this entire introduction of aerodynamics? Very vast area he covered. Like each chapter itself is a specific research area, and he covered
Yeah.
every chapter, not every chapter, every week as a research area he covered. So, uh, like I just want to know your understanding, like which area is more attracting to you in his lectures.
The area with the shock part, like studying of the shocks and
Okay.
how do they get developed. I mean, the supersonic flows, and then sometimes they get turned into subsonic, and even if we have a subsonic flow, that may get turned into a supersonic, and that the shocks may get developed on the wings. Or I mean, it's generally very important in studying like different components as well.
Yes. And
So
you are
that we
like,
can,
yeah,
sorry,
yeah, you can please continue.
so that we can avoid them and do our design so that we can avoid some damage. Even the
Okay.
wind tunnel studies, how that can be performed, not just the aeroplanes, but
Hmm.
even automobiles, everything, the aerodynamic study to avoid shocks. So that is very interesting.
Okay. So during your time, if I'm correct, in RVRJC or not RVRJC, in Siddhartha, I think aeronautical is there, right?
I'm not sure about that.
Okay. So around which year your graduation?
I graduated in 2012.
2012. Okay, nice. Thank you, Kavadi. Let's ask Arhit. Arhit, do you have any very interested areas so far?
Yes, sir. Hello,
Yeah. Let me know
sir.
what
Am I?
areas that you. Yeah, you are audible.
Yes, sir. Actually, I am interested in basically biomimicry, and we can say, and technologies like morphing wings and CFTs. So I'm interested in this type of concepts like morphing wing. How means adaptive wings. How can we biomimic like the flight of birds and all? How can we biomimic and we can make those mechanisms mechanically or aeronautically? Means a mechanism we can build, and using that we can perform various analysis. Or I am also interested in supersonic flows and the CFDs behind it, the CD nozzles and all this.
Okay, interesting. So, without any delay, I can start today's session.
Yeah,
Let me share.
sir, 1 second. Before starting, I think in week 10, one of the lecture is missing, 57.
Week 10:56. Let me check.
Hello, sorry sir, my connection got lost.
It's okay. You are audible to us. Week 10, lecture 57. I think someone raised this query. Is that you?
Yeah, I only
Developer.
raised.
Yeah. Okay. Okay. So I have no authority, I mean, access to change those things, but I can forward your query or to the concerned professor or concerned NPTEL team.
Okay.
If that is like problem for you or I think everyone is facing that. Let me see that once. So just let me share my screen. So you both are going to give the exam also, right?
Yes, sir,
Yes
I'm
sir.
going to give this.
Week 10, lecture 50. Oh, lecture 57 is not here. I'm also unable to see this. So we are already here at the flow isolation techniques, Liren, Rayleigh, Pitot, okay. Okay, can I call you Mrs. Comedy, right?
Yeah.
Yeah. So I will forward this query to the concerned persons or concerned team of NPTEL. They will look into it. Like I will forward to professor and team also.
Okay.
Possibly they will try to resolve this.
Thank
Maybe a
you.
technical error or yeah. Okay. So any doubts other than this before starting this session? Any doubts in all those any week and last weeks or previous weeks uh, discussions or the lecture content or any topic that you want to learn more?
Yes, sir.
Yes,
Hello.
sir. Yes, yes.
Sir, I was speaking of that flow visualization, that oil flow visualization technique, and another thing that's Schlieren technique. I am not able to understand that Schlieren technique, how they are modeling it. Schlieren
Schlieren
and
technique.
shadowgraph.
Schlieren shadowgraph needs some understanding whether I don't know whether it is clearly professor definitely clearly. I mean, whether it should given a overview or not, or
Yes, sir.
they give you the
Professor has given an overview, but I
okay.
think, sir, if there was an animation of how Schlieren technique or shadowgraph technique is used, I think it
Mhm.
would have been better because I was not able to visualize it. How?
Visualization you can do by two things, like not two things. It's a only primary principle is like you understand the primary principle. What is
Yes,
happening?
sir, I
Why? How?
understand.
Where?
Yes, sir.
What is that?
Yes, sir. Sir, actually, in Schlieren and shadowgraph, they are using optical and collimatric lenses. I'm
Hmm.
not understanding how they are managing to get that on that screen. Actually, the data.
Hmm.
How will that? How will anyone get the data from Schlieren and shadowgraph technique?
It's a two things that is happening in the Sheeran and shadow graph. One is, I mean, why they are two different is the only parameter that is playing is a density,
Yes, sir. That is law of
and that is
refraction.
yes,
Uh,
density is the only parameter that is playing there. So what they are trying to do is in this Sheeran or shadow graph, you just go with the shadow graph. Let me see that. Let you see the shadow graph technique. Let me share the screen to you. Just give me a second. Just a second. Still uploading. You can see my screen, right? Ajit, can you see the
yes, sir.
screen?
Yes, sir.
Yeah.
Yes, sir. Yes.
It's, so you see this one.
Yes, sir. Sir, you are not audible.
Hello, can you hear me?
Yes, sir.
Okay. So you have to get good understanding of how this entire optical system is able to create the virtual image of your actual test section image. Suppose if you have an object here, the region object here, you are now carrying out this image based using this optics and to the virtual screen or a camera here. So to carry this image, depends on all your optics arrangement, how you are doing. But the principle that is creating the required phenomena that you would like to see is depends on two things. For the shadow graph that you are doing with the first gradient of density, as the light is bending due to the density gradient in the flow. Because if you light should pass in some media, right? If it is as it passing through, if it is experiencing some kind of unconditional situations like the shock regions, as it passing through the shock regions where your density is uh, varying very huge, or its gradient means the change in density, right? At that particular portion around, if you see the shock region, it is not uniform, or it is not like continuous also. It is very discontinuous at that particular region. Are you aware of that?
Yes, sir.
Yeah, that is
Sir,
causing
actually,
that. Yeah,
sir, I think this Schlieren and shadow graph technique will be basically used for high Reynolds number and higher supersonic flow, as per my assumptions. Because, sir,
it's not
in that
assumption, it's
case,
true.
the
Yeah.
compressible, if there is compressible flow, that there is density change, and due to that density change, there will be reflection of light.
Yes, that is the only
Yes, sir.
principle how this shadow graph and Schlieren is. If there is
Okay.
no density gradient, you are unable to see those kind of shock waves or its actual position. Like you can see this at shadow graph. Okay,
Okay, sir.
therefore shadow
Sir,
graph
but
is sensor.
but the
So
thing is,
both, yeah.
sir, in case of Schlieren technique, they are using a knife edge.
Mhm.
Sir, don't you think that using a knife edge will create
Okay.
diffraction of light in that case?
This knife edge is like to determine and more or less like your focal point. This knife edge you are looking, right? Like
Okay, okay,
how,
got
what
it,
do
sir.
you understand, because based upon the use of knife edge there at this point?
Sorry, sir.
Okay, if you are not, what do you understand the use of knife edge in this optical illustration, optical
Sir,
techniques that you learned to?
I thought this knife edge was used as a means obstacle in the path of that light rays, and it was used for diffraction of light. I thought like that.
Instead of okay, okay, let's not worry about the use of the knife edge in this system. But if you want a more details of it, I will clearly show you some animation videos. Maybe hello.
Yes, sir. So actually, hello. Hello. Hello.
Are you hear me now?
Yes, sir. Now I can hear you.
Yeah, there is a certain fluctuation in the network.
Yes, sir. Yes.
Okay. this shadow graph and Schlieren technique, we have experimental facilities available also here in IIT Kharagpur. But to get you more details, I will show you it's maybe in the next class for your detailed understanding. If you still need more understanding of experimental visualization and theory of this, I will give you the idea completely in the next class with a video, okay? And how this optics will work. I will
Okay,
print
sir.
the construct and then we'll show you.
Okay, sir. Sir, another thing I want to
Hmm.
ask, in that water analogy, what they are
Okay.
using the fraud and that Mach number analogy. In that case, is that water flowing at a high speed?
Which analogy?
Sir, in this PPT only, there is an
Okay.
analogy of fraud number and Mach number. That is
Okay.
water and sound analogy. I think can't recall that heading, but the concept was like that only. They are using that analogy to visualize shocks and expansion fans.
Yeah, I did not go through that. Can you tell me
Yes,
like exactly where it is?
sir.
Fraud analogies.
I have to go through the PPT one, sir. Sir, in
Okay, let
lecture
me
first and the second, no, before relay Peter tube. Before relay
before
Peter tube.
related
Sir.
to is that
Yes, yes, sir.
explained on notes? I mean, whiteboard.
No, sir, no, sir. There was a picture of it.
Boundary
A
layer
wedge
flow.
shaped, object was there before this, sir. Before this lecture, yes.
This one, mounting arrangements in the winter section.
Before this, sir.
Vertex generation.
Before the arrangement and all. The first lecture only, I think so, Professor has. Yes, sir. This one, sir.
This wedge.
No, not this one. This is Schlieren technique. Before this, I think so. It will be.
The dye visualization that you are asking.
No, no, sir. Before this. No, sir. Before this. This one, sir. This one.
Fraud number.
Yes, sir. Yes, sir. Yes, sir. Pre-surface flow visualization.
Pre-surface. Oh, surface flow visualization you are asking about.
Yes, sir. Yes, sir.
Hydraulic energy.
Sir, in this case, means how the flow is generated. It is a very shallow water is passed through that object to determine all these shocks and expansion fan. Means how it is generated, sir, how the water flow is generated, and secondly is, sir, whether it's the flow of water is streamlined or turbulent. I think, sir, it is streamlined in this case.
It is analogous, like it is not actually supersonic flow. It is just analogous. If you see from the free surface flows, we've been discussing about these finite waves of like acoustic waves. Also, we are discussing, right?
Yes, sir.
In this free surface flows, only we are like with my understanding. I'm telling you because I have never used this hydraulic analogy of free surface flows, but with my understanding, I'm telling this. Whatever we are studying in the theoretical class, like about the finite wave concepts or acoustic waves disturbance that you can see in the visually see in the uh, free water surface flows. That is what they are trying to replicate. Like if you are having any disturbance in the free water flows, you will see ripples kind of things. That those are nothing but sensing of a disturbance in the in the water flow, and those disturbances are acting like a passing. That information is passing to the next molecules using these waves. That if you drop any kind of disturbance in the water flow, how it will distribute. You can see that, right? Those ripples will
Yes,
disturbance
sir.
will propagate to all over
Yes.
the surface. So that is what they are trying to analogy. Like even it is a media is same. Like if you are going for the high speed flow, the things are like very strong enough to make your density change of properties. But if you are low speed flow and you want to like just analogous means that you are just trying to replicate the idea, but not the same quantitative information. Sorry, qualitative information. So quantitative information, not qualitative. Quantitative means that you are not measuring anything. You are just visualizing how the effects will be. Here in this wedge, you see they are trying to replicate the front propagation of these normal kind of some waves that generated because of the leading edge and some other waves that is generated at the corners. So even if you go for the very high speed flow, the wave propagations are more or less like the same that we are visualizing in the surface flows. That is what we are trying to replicate, but not it is uh, like exactly same as the shock waves. Is that what you want to understand? Like any other details that you?
Yes, sir. That only.
This is not vastly using, I guess, but just for the understanding of how the object is creating the disturbance and its waves propagation. Even if you're studying in the theory way, it may not give you the all details how these waves will propagate based upon your free stream flow or based upon your uh, like the conditions, the free stream environment conditions you are creating. But if you are trying to replicate with some free surface water flows, you can get some idea how these waves are distributing inside the in the flow. That's it. Like even if a ship
Okay.
is going inside the water, you can see the wave propagations in that. Have you ever observed that a ship or a boat is traveling in the water? You can see the ripples in the wave and the water free stream in the river. So those are also analogous to like it's a not a finite variation or not. It is not generating any kind of significant or like negligible also like disturbances of properties or change in properties. These are just passing the information and its structure is the same that we are discussing even in the hypersonic flows also. That is what the author is trying to convey, I guess. If it is not correct, I will just revise this again. I don't recall that whether I studied this or not, but I will just recall this one, hydraulic analogy. But similarity is like the same one I'll just discuss with you. Okay, this one also I will keep a note on it. Hydraulic analogy, and I have to discuss this Schlieren and shadow settings. How to show you how it is happening. Okay, any further things?
No, and another thing, sir, in the first page of the PPT, that is oil flow visualization. Sir, I am not able to understand that pictures, this type of pictures, how it is getting, and the picture in on the right corner, sir. I was not able to understand this also.
This oil flow visualization is basically for supersonic flows. They are trying to see where are the attachments and reattachment regions. Only you can very clearly see. So if you have a uniform flow field, like without any disturbance, you cannot see any uneven distribution of oil in flow field. Like if there is no object in this, let's say consider the first image. If you don't have any kind of object in the supersonic flow or whatever the flow it is, and do you think that oil will give you any kind of patterns in that supersonic free flow?
Hello.
Are you able to hear me?
Yes, sir. Yes, sir.
Yeah, I'm just asking that if you are having no object in the free flow, like any free stream flow, and you are have coated the oil on the surface, do you think the oil will give you some kind of patterns because of this no disturbance and only uniform flow?
No, sir.
There won't
I
be,
don't think. If
yeah,
you,
you don't. There won't be any patterns in the free stream, like on the oil, right?
yes, sir.
Now like it's up it's now I will just ask you like now you are placing the object and the flow is supersonic. What are the phenomena that you can see in the supersonic flow phenomena that you can understand like the supersonic flow?
Sir, in case of supersonic flows, we can see shock waves, expansion fans, and
Shock
wake
waves expansion
formation,
has yes
formation of
so
wakes.
fine. So all these things I am able to see here because your object is blunt. It is not a sharp and it is very blunt. It is creating a bow shock because it is a supersonic flow. Bow shock some distance ahead from the object. So this distance and it is creating a bow shock here. So you are seeing the discontinuity in the oil are a kind of pattern. So what it is doing is whatever the elements that are coming here, it is creating a kind of discontinuity layer and the remaining fluid, it is acting in another kind of way because your velocity decreases very huge. All the oil is gathered here and form the shape of how the fluid flow is behaving. You see, discontinuity is representing your bow shock here. You can see, you can just relate with your bow shock because there is a discontinuity. It is creating the pattern that as the bow shock is appeared there. And this can be another, but I don't think it can be the another shock, but let me see, is there any physical phenomena they are displaying, explaining about this? Are you able to understand what is this discontinuity?
Yes, sir.
Any,
Shock. Formation of shock, I think so.
are you sure?
Formation of shock. No, sir. This is, I think, the flow separation happening here at that point.
Yeah, that could be. This maybe a flow separation because already we have a shock here and it is a bow shock. The possibility is a flow always like it can act as already a subsonic and to here because your body is a bluff body and possibilities of more separation on the upper surface. So it can be form a separation also on the upper surface and you can also see formation of horseshoe vertex kind of phenomena. It is not very clearly able to see on this oil flow visualization, but maybe with your further analysis, you can say that this is a horseshoe vertex, and because of this vertex, you are able to see another kind of two vertex. The influence of primary vertex is able to generate another secondary vertex also. So this kind of uh, possibilities that you cannot entirely see that, but with this understanding of patterns, you can see some phenomena or some discontinuity, either it can be separation or this can be reattachment is happening at this particular portion. Or in this image, you can see also the wake region, how this wake is distributed, and you can see a converging portion and diverging portion of fluid also. In behind this wake, the fluid is coming here and it is converging and it is like trying to enter into the wake on after entering into the lake again it is this diverging like this. So these kind of qualitative features that you can able to understand from this oil flow visualization. Many interesting facts in the low speeds what people used to do is for identifying the separation lines and reattachment lines, where in the high speed flows you can also see patterns of the shock waves also. Now you are clear, Arhit?
Yes, sir. Sir, in the right corner, there is a picture that formation of the horseshoe vortex you told. Sir, in front of that bow shock, there is a horseshoe vortex. In the second or the
This
third
pat
picture, we can visualize it. I think that is only the horseshoe vortex.
this pattern. I'm also thinking about this, but the thing is, it is not very clear because it needs to uh, separation and reattachment kind of phenomenon that we should ensure that whether it is really the horseshoe vertex or something else. But we can relate that those two and how formation, like where it is separating, it can be this line is can be the separation line of this horseshoe vertex. And why this horseshoe vertex is forming also, we have to ensure that what is the causing mechanism of forming this horseshoe vertex in the supersonic flow. So it can be sometimes it can be a spiral also, not a vertex. We have to differentiate. Many features are there. I don't want to confuse with you spiral and horseshoe vertex, but if it is really horseshoe vertex, another separation kind of like whatever the discontinuity presented here, here also one more discontinuity will present. And why it is discontinuity is present is like are you able to understand like the idea of separation? What happens at the separation?
Yes, sir.
Well, like you can mention any mathematical formulation of
Sir,
the
that
separation?
adverse pressure gradient is the main cause of flow separation. That you were asking, sir.
Do you know about this one?
Yes, sir. Yes, sir.
D, I will say you. So if you have any separation point is happening at any particular location, you will get a zero velocity there, right? Or this gradient will also become zero in the y direction.
Yes, sir.
Yes. And
And
your
now,
skin
I
friction,
think, sir, I think after that separation region, this gradient becomes negative. That is,
yeah,
we
that
call
is
it
one thing.
adverse.
Yes. So as your velocity is going to zero, your shear stress, that is the skin friction on the surface, this skin friction is also going to be zero if it is really this particular portion. If it is really a separation line at this portion, your skin friction is also going to be zero. That is no effect of fluid at this particular region. Until this, the fluid flowing out above the oil is dragging this fluid. Like dragging this fluid means dragging this oil also because of the resistance. But at this particular discontinuity, what is happening? Your fluid is not dragging the oil because here your separation is happening, right? So since it is not able to drag this fluid as a separation happened, you will see a formation of pattern at this line. And after this pattern, your fluid will drag in another direction. The direction based upon how your velocity gradient is behaving at that point. So that is why you are able to see patterns in the oil flow. This because of this derivative of velocity. You understand that?
Yes, sir.
Yeah, it's velocity gradient. Depends on your velocity gradient. If you are having no velocity gradient at that particular location, the fluid, I mean air or whatever the supersonic fluid, it cannot drag the surface oil, whatever you already applied on your object on the test section. So since it is unable to drag that particular portion, it is the shapes are creating and we are able to see the patterns. This is the basic principle why we are using the oil flow visualization. But you see, there is no indication of this expansion waves. Are you able to see any indication of expansion waves?
No, sir.
I don't see any indication of expansion waves because it is like expansion of the fluid into the it's just increasing of its Mach number because of this expansion waves if the fluid is supersonic there. And this expansion, yes, constant and there is no variation of any velocity gradient here. Even though velocity gradient is varying, you don't have any zero gradient to understand or any strong gradients present at that particular point. These are smoothly the gradients varies on this along this expansion waves are very smoothly. Those are not a discontinuous ones. So it is not very clear to visualize expansion waves of this oil flow visualization. Okay. Any further discussion?
Yes, sir. Another question I have.
Okay.
Sir, in the last assignment, assignment 9, question number
Assignment.
2.
Let me open it. Assignment 9, question number 2. Okay, any is it? Let me see first.
The date has got over.
Sorry.
Sir, the date submission date has passed. Sir.
Okay, just I will just see that you're asking some. Submission date is past, but let us see what is the question. If I can answer that, I will answer it now. Which lecture it is? Like week 9 or which week?
Sir, week 9.
It's a week 9, and what is as a week 9 assignment? Okay, question number 2.
Yes, sir. Question number 2. Sir, A, B, C, D all are correct. I think I have chosen only B and C for the correct option.
If A, B, C, D or all are correct, and you chosen only
B and C, but I also think that A is also correct. But sir, option D, that it reduces fan noise, I can't understand why it is given.
The length of the diffuser of a low-speed wind tunnel is found to be greater than the length of the contraction section because it improves the efficiency of wind tunnel. Yes, it prevents the flow separation and the diffuser. Yes, it reduces the adverse pressure gradient. It reduces the adverse pressure gradient. If you keep the more length, then you can decrease the divergence. It reduces the fan noise. Looks like all are correct, right? Which
Sir,
point
the
you
last
missed?
last option, it reduces the fan noise.
It reduces the fan noise. Like you are creating the tunnel and making it the length very long. It's a simple
Yes, sir.
analysis. Like if your waves are traveling for a long distance, what will happen if it's sound effects? It's suction effect. If you are putting very short length, the flow that itself you are creating very turbulence kind of thing, right?
Yes, sir.
The divergence length. The best way that we can explain, maybe it comes with your experience of you analyzing. Like if you are putting very long length and very short length, you will hear that difference, how much of fan noise that you can see. But this option is also looking correct to me, like how to explain it in a theoretical way.
So I missed that option D.
Okay, the air enters very smoothly, that I can say, without having any creating any kind of turbulence, or air leaves very smoothly. Both things can happen with your long divergence section. Is it?
Hello?
Yeah.
Sorry, your voice is breaking. I think.
It's maybe because of the unstable internet today. Very sure why this is happening. Is it clear now? My voice is
Yes, sir.
okay. So any more further questions you have?
No, sir. No, sir.
Fine. So you missed this option. It reduces the fan noise.
Yes, sir.
Yeah, we are just creating a chamber to allow the air very smoothly. So possibilities are like to reduces the noise also. Like if you see the uh, jet engines based upon the shape. Like have you ever seen the jet engines also? Based upon its shape and based upon its length also, the fan noise or the noise that is coming from the jet engines can also be reduced. So the length also affects the divergence
Yes, sir.
section, whatever, because if the heavy fluid is coming throughout from the section, uh, we can, like acoustics are different that based upon, we have to design based, like the designs also based on the acoustics that are generating inside the test section also, if it is very carefully designed also, right? For a low noise, people have, this is very vast area, like how to reduce the acoustics noise that is generating inside any flow that is exiting from either subsonic or supersonic. If you are creating exit flow, you can nullify the effects with a long divergence section that you can better understand when you have the practical experience of seeing any flow through a convergent divergent sections. Have you ever, like, if you seen, have you ever seen, have you have opened facility or something? You are from Punjab Engineering College Aerospace, right? Is it?
Sir, me?
Yeah.
No, no, sir. I'm not big.
Then you mechanical,
Yes, sir. I'm from mechanical engineering.
and you have aerospace engineering department there.
No, sir.
Punjab, I heard that there is mechanical, sorry, aerospace. Okay,
Sir,
fine.
Punjab Engineering College is aerospace engineering. We don't do.
Okay. Oh, you are from different college.
Yes, sir. Yes.
Okay, that's my mistake. So, uh, like if you strive, like if you have a possible days, or else once you have the chance to see any flow through a convergent and divergent section, you can hear for short length and long length kind of experimental facilities, how your acoustics also and noise generation are different for your different lengths of the models. It's a kind of practical explanation I can give you, but I have no much idea on how this acoustics is, like the sound waves is nullifying if the length is so long or so short. But this is a really big area of research that one people have been trying to reduce this acoustic noise by trying to keep the short length or trying to maintain the less noise that is coming from the jet engines or any nozzle flows or anything. Okay.
Okay, sir.
Yeah. Now I think I will just give you the overview of last week. But any more questions?
No, sir.
Okay. Fine. If no questions, any other questions, anyone?
No, sir. Go ahead.
Yeah. Okay. So if no questions, I will just show you the review of the last class, what we have done. In the last class, we just like solved some problems on the finite wing concepts, and before solving that, we just discussed things on how to generate, like how to deal with the theoretical aspects of this finite wing and wingtip vertices kind of aspects and inducer drag kind of aspects. So, and then those problems we solved in the last class. These are all just a recap of those problems we discussed. Many problems are discussing about the theoretical aspects instead of numericals. And then also we discussed, I think I cannot, okay. And then also we discussed how to identify any kind of aerofoil that we have in experimental situation and how to make that in, how to measure its chord length. Like if you have a random aerofoil given to you for your practical analysis, we need to configure like what is this aerofoil detail, what are the aerofoil details, like its camber, chord, thickness, everything we need to first measure. We need to quantify those, and then we can proceed only for the corresponding experiments based upon this coordinates. So we also discussed that how to generate those kind of coordinates, like not to generate, but how to identify these coordinates and how to proceed for the experimental analysis. So, so those are the details that we discussed in the last class. And today's class, we will see some more problems on this shock waves kind of phenomenons, and there are some problems in these high speed flows. So we have few problems in this entire section that we are going to solve today. So before solving this problem session, I will just give you, like, I will just show you the lecture material. The PDF. Final method. We can just have an overlook of that. Open board problems and week 6. Just remember if it is not downloading. As we are having a delay in this complete details of covering the problematic, we will go through the problematic details. So in the upcoming sessions, 3 more sessions, we can cover all the problem solving discussions. So this is a today's concepts that we are going to like just, I will just give you some, if there are important equations in the slides, we can just mark those equations and those things we are going to use for today's class. And so the things are like this. We are mainly focusing only on every details that we are focusing here and only on the perfect gas. We are not going to any other real gas kind of situations. Mostly for all our ideal perfect gas assumptions, is we take as the air is our that we are considering air as our perfect gas and dealing all these problems in this particular session. Like, or also we discuss the same thing. A professor has discussed the same thing. It's post content also. We are dealing with only air and those properties, those constant properties that universal we use, that universal gas constant we are using it mostly for all our problem solving sessions on this theoretical aspects of these high speed flows and specific gas constant also. These two are related to our entire discussions. We are using as a constant for learning this chapter. And useful or standard kind of forms are everything that related to your temperature in this kind of. Until now, we haven't seen any temperature effects in the entire theory, or we have this, you had learned so far in the lectures. But in this concept, our entire content relate moves on this main one equation. P is equals to PV equals to RT. So entire concept P equals to water, PV is equals to RT. The entire concept is relating on the pressure, density, and your temperature. So the first thing is whether it is we have to define whether it is calorically perfect or thermally gas perfect. So those definitions also we clearly mentioned. The gas we are taking it as a calorically perfect. That is, we are not taking anything that is really like these constants, the the gas constants or this constant pressure and constant specific heat ratios, also heat addition rate per unit kg or uh, that unit as a constant pressure or constant volume. This heat addition rate required for raising your unit temperature. So these things we generally denote it as Cp or Cv. So these things also we are taking it as constants and we are not varying with any kind of temperature effects. We are not dealing with variation with the temperature. Then it will give you a nonlinear problem. And we also know that internal energy is a function of temperature. Both enthalpy is also a function of temperature. So internal energy and enthalpy also we need to deal here, so that then only we can frame our entire concepts of this one-dimensional flow of it. And you should also remember that whatever the things we are all dealing, these are all only one-dimensional. So this is not writing good. So we are dealing only with the one-dimensional, and very important formulations are the Cp is equals to that we are relating with the specific heat ratios, that is gamma R by gamma minus 1, and Cv also we are relating with the specific heat ratio and the characteristic gas constant. So these things we always need to keep in mind while solving the questions. And first law of thermodynamics and what is adiabatic process, reversible process, everything that you have learned already in the basic thermodynamics. And idea of entropy also. This formulation is really important, and this one to find the change in entropy or the calculations that we are going to do across the shock waves also. These formulations are very helpful for us. And then this is a key relation that we always use for our normal, not in the normal shock wave conditions, for our no heat transfer, like in the free stream flow kind of conditions, like before the shock waves and after the shock wave conditions, we can apply this kind of relations and we can find its properties at that particular point based upon 1 and 2. And then this is all, like you see, this is all derived based upon your assumption of isentropic equation where your ds is 0. But in your real life, your isentropic is never, I mean, the change in entropy is never 0. So it is always at some finite value and increases in a positive manner. And then, but for our theoretical aspects, we stated it as a 0, and continuing for derivation, we ended up with this particular kind of relation. and we can use this before the shock wave and after the shock wave, but not across the shock wave. And a very important concept that we derived the sound wave equation starting from the idea of compressibility. We start with the idea of compressibility and we use that to formulate how the area ratio can be related with the compressibility. That compressibility we say is a change in volume. We start with the compressibility there, and then we use that to frame this kind of particular formulation. This is also for the isentropic conditions. And then here also some many important basic levels that we need, all these formulations we need for today's problem solving session. So I hope you all aware of these kind of formulations, like how Mach number is framed, and I mean the definition is framed. I mean Mach number is the velocity by sound velocity, and here the sound velocity is defined as its square root of gamma RT. You can see this derivation also, but just we had seen how, well, like from this a square, we know that dou p by dou s at constant and so entropy condition. So using the same formulation, we derived that sound velocity equals to the square root of gamma RT. This is another important relation that we use always in any problem solving of this particular week lecture. And then we have important relations that related to the normal shock wave, oblique shock wave, everything. I hope you are aware of that, but we'll just go through those kind of formulations here, because as we are discussing those things primarily in this lecture, this is the velocity potential equations mainly applicable for supersonic flow kind of conditions. That this is derived for that particular condition only, where your flow should be inviscid and it is a compressible kind of relation. We derive this kind of potential flow, I mean velocity potential equation for the subsonic kind of conditions also. But at this time situation, we only ended up with Laplace kind of formulation instead of you getting this entire big frame of equation. We ended up with only simple Laplace kind of formulation. So it is always important to correlate with your high speed flows to your subsonic flow, because if you neglect some terms that is related, that those are related to your high speed flows, then mainly in the high speed flows you always deal with the Mach number. So whenever you see some equation in the high speed flows that is related to, if you remove the constraint of Mach numbers, like if you want to transform that relation into the subsonic flow, you just need to delete any parameters, or you just need to nullify those parameters that are related to the supersonic flows or the high speed flows. Then you can get the same formulation that we already derived for the subsonic kind of condition. The best example is this velocity potential equation. I think that already discussed in this lecture, how this velocity potential equation, that one, if we remove some particular terms, that can be easily transformed to velocity potential equation in our subsonic flows. This is the Laplace equation. You can see we started with in this lecture they started with velocity potential equation that related using the assumptions of a compressible flow. But if we set this sound velocity is tending to infinity, which is our main criteria for subsonic flows, like we said in the sound velocity as tending to infinity in the subsonic flows, which is theoretical applying. If we substitute the same in this complete equation of our velocity potential, then you will end up with this Laplace equation, which was we derived already in the year in this subsonic kind of concepts. So except this Shockwave kind of formulations, you can relate any governing equations to subsonic to supersonic, and those are still valid up to certain level. And we have to also see the assumptions that given for this deriving any formulation in this kind of particular chapter, because many formulations are started with the governing equations of continuity, momentum, and energy. So all these governing equations, first, if we are deriving for the shock wave kind of characteristics, we will start basically with the momentum, and then energy equations that basically involves the only for one dimension formulations. And those you relate the current situation of like what is the problem, whether you are dealing with a normal shock wave or oblique shock wave, you start with those equations and you apply the conditions that we have that in the problem, whether you're dealing with a shock wave, normal shock wave, or oblique shock wave, then you will get the final formulations. These are, even though you don't have a formulations, you can start up with always your governing equations like h1 plus u1 square by 2, like h2 is equals to h2 plus u2 square. Let me show those equations are here or not. This is also one. This is the one I'm talking about. If it is CPT1, CP indicates the H1, and the CPT2 indicates your H2. So this is your energy equation. So you can use this all anytime to apply for normal shock waves or any kind of situations. This not only just momentum equations, momentum conservation, and also the mass conservation also you can apply using those conservations all the time. Keeping analyzing the problem correctly. We are we are just simplifying instead of using many terms, we are just simplifying our requirements by stating the stagnation pressure kind of conditions, static pressure kind of conditions. We want to directly obtain the corresponding properties without always going to the conservation laws, and then so that's why we have always ended up with the simple algebra form of relations that involves only the Mach number, or that involves only the stagnation pressure or the static pressure. So these are the primary relations if you are dealing with only the isentropic kind of flows or isentropic kind of flows, like where there is no shock waves from shock waves that you are interacting with. But if you are interacting with the shock waves, there are very complex kind of relations that you will encounter. Where if you have a shock wave here, normal shock wave here, and if you are encountering a Mach number like your supersonic Mach number is m1, you will see the subsonic Mach number behind the shock waves. Note that it is a static or a non-moving shock wave. Then you will see the a Mach number with flow with less Mach number, that is subsonic levels, and this is supersonic levels. Okay, this is supersonic and subsonic levels. If you have a supersonic Mach number across the shock, that will become easily subsonic. But note that it should be these things are applicable only for your shock waves, normal shock wave, and you can also transform these relations that will that in terms of the oblique shock waves also, like transformation in the sense oblique shock wave relations also in the similar way, but we need to resolve our flow directions to apply these equations that we also will see in today's session, how we can use these relations for oblique shock wave also. And this is the pressure ratio, static pressure ratio relation across the shock wave, and this is the temperature relation ratio. And this is also your governing equation. Basically says the Huguenot equation. So this is also we are not using this Huguenot equation in the problem sessions today. And then oblique shock waves also we are dealing today. We will just see how to use the normal shock wave relation in the slide that we see for the application of oblique shock waves. And then convergent divergent section where you like the static pressure or the stagnation pressure in a big chamber, and you are releasing this entire flow inside this high pressure chamber, that is a stagnation pressure P naught. And if you are releasing it through the convergent divergent section, we will also deal these kind of one or two problems on this relation. And I remember that I think we discussed about this area rule with the change in Mach number, with the Mach number relation and velocity relation, how it is affecting our entire flow physics for difference from. I hope you are able to hear my audio, right?
Yes, sir. Yes, sir. Yes, sir.
Okay. So, this relation is very useful to deal with how flow is varying in convergent section and divergent section, whether it is low speed flow or high speed flow. Based upon that, your Mach number, whether it is accelerating or decelerating. I hope you studied that. If the flow is supersonic, how it is behaving divergent section,
Yes, sir.
or how it is behaving in convergent section. So we will be using this particular equation. And this is also maybe needed. So all these are just for your understanding how we are using these equations. If you don't know the derivations of those things, it is not a requirement, but you need to understand how these equations are affecting the each parameter, the influence of each parameter on another parameter, and how theoretically you can relate that. If you are interested to learn all those derivations, you can go through the you can come up with the advanced classes, and you can learn with in those advanced gas dynamics kind of lectures. But it is now interested topic of understanding these relations effects in the problematic or a real life kind of situation. So these are also, and this is a kind of choking that Professor has explained here, how the mass flow rate choking happens when you increase the pressure and the inlet pressure to very high levels. Even though increase it to very high levels, it cannot deliver more mass flow rate as it is already choked. And the boundary layer effects and its incident shock wave. If there is any oblique shock wave that is incidenting on the boundary layer, how the phenomena looks like, also he explained here. Yeah, more or less these are the contents that hypersonic flow may be slightly uh, touched, like how the equations are differ for the hypersonic flows. Just briefly explained here. And the effects of shock tube also, I guess he explained in this lecture. The use of shock tube and how we can create the moving shock wave, and we can analyze this experimentally also. We can build an experimental shock wave, and we can analyze the properties of the shock wave based upon the conditions like experimental facility we have. We can analyze those properties of normal shock wave, and we can validate our results also. So more or less, these are the contents. We just reviewed equations only. How this entire chapter is going, entire week session is going on. So now we will see those kind of equations and its their problems related to these concepts in this particular lecture. So before discussing, I just let's just take a 10 minutes break, and we will meet again at 7:16. Is that okay?
Okay, sir.
Okay. Let's
Yeah,
take a 10
sure,
minutes
sure.
break, and yeah, sure. We can meet again. hope you all are here. Am I audible?
Yes, sir.
Yes.
Yes, sir.
Okay. Fine. So if you all are here, let me start this session. So, Arhit, have you seen this question previously? Like, have you solved it in your assignment sessions?
So
I
this
don't know
one,
whether these questions are repeated or not. If like let's say I just ask you I will just not only Arhit, if Mrs. Comedy is also here, then we can just discuss it. Like how your thinking
Yeah,
Sir,
perspective
these-
is. Yes, yeah.
sir, this
Give it.
question is repeated, sir. Yes, sir.
This question is repeated. So
Root
let me
over
frame this question. Yeah,
yes. I
let me
think
frame
that
the
formula
question
root
for
over
you.
gamma t we can use.
Root over gamma t. So, Mrs. Kaumadi, you also like submitted this question. Like, I don't know because I did not go through the assignment. I have some certain kind of questions given for you to discuss with you. Uh, we are just discussing
Yes.
today. So, I think you also solve this question.
Yeah, I have also seen this.
Yes. So, the basic idea is it is discussing. Yes, can you frame this? What is the? Let me read the question first, and you can discuss that. The question is, you have given when they have given you a diffuser section. I think you know the diffuser, right? I need to explain this diffuser section. So in this diffuser section, they are only stating about the diffuser section. The wind speed is around 380 meters per second, and speed of the sound and the Mach number at the diffuser inlet when the A temperature is 40 degrees Celsius. Assume the gamma equals to 1.4 and R equals to 287. So how can we proceed for this? We need to find the sound temperature and Mach number. Sorry, sound velocity and the Mach number. Harshit just told that we can use a square root gamma t. So we have t. Yes, t equals to 40 degrees Celsius. But can we submit t in the degrees Celsius itself?
No, sir, Kelvin.
It has
Because
to
R
be
is given in Kelvin, sir.
Yes. So it has to be in Kelvin's format. So we should submit that temperature in Kelvins only. This is defined for R is defined for the Kelvins only, and this is a non-dimensional one. And given that we have gamma also and R also, so that will solve for our like the sound velocity. If you solve that, you will get the sound velocity of 354.63 meters per second. So in general sense, what is the sound velocity in air? Do you have any rough idea?
330 meter per second, sir.
330. Okay. Kaumadi?
Hello?
Yes. You have any general idea of what is the sound? What is the sound velocity
It's
in air?
around 3 into 10 power.
Okay, something
Can
around
you-
say 3. Yeah, I can 3 into 10 power.
10 power 6, if I remember. Meters
Sound-
per second.
No, it's too high. We are just having around 340 to 330 to 340 meters per second. Depends on temperature effect. It slightly varies there. So around 330 to 340 meters per second is the sound velocity in air. We are discussing. So, but if we see this particular sound velocity, it is around 354, and the local velocity is 380 meters per second. It is very clearly able to understand that it is a supersonic flow, 380 by 354.63. This will give you the Mach number. So what will be the Mach number? Will it be greater than 1 or less than 1?
Sir, greater than 1.
Greater than 1.
Greater
It's a
than
fraction.
1.
Yes, its fraction is clearly greater than 1. So it is the supersonic flow. And the question, one more question I just want to frame is, since your Mach number here is greater than 1, that is a supersonic flow, and if the flow is like I am telling, the flow at the exit is less than 1, Mach number 1. So what is happening in this diffuser section? What phenomena should happen if this case should be true? My diffuser inlet is having, yes.
Please,
Any
please
idea?
go ahead.
My question
I
is,
think it
I'm
depends on the pressure at the exit, the diffuser.
yes, it depends on the pressure exit. Also, you can modify the inlet pressure also. But what phenomena should happen inside this diffuser section? If my Mach number at the inlet of the diffuser, say at this particular portion, is greater than 1, and at exit, my Mach number is less than 1. What should happen in the diffuser section to make this true? Because we know that as if the flow is supersonic and it is entering into the divergence section, the Mach number should increase. The flow is expanding here. If the supersonic flow is expanding like this, the Mach number should increase. That M should be more and more. Like it is now say 1.07. It should go to 1.2, 1.3, like that. It should increase. But finally at the exit, it is less than 1. So what should happen? What phenomena should occur inside this diffuser section?
Hello, sir.
The velocity of the air should reduce. So,
Velocity of the air should reduce. Okay. Arhit?
Back pressure, I think, sir.
Pressure. So you just look at the only Mach number I'm telling. The Mach number is supersonic here and Mach number is subsonic here.
Yes, sir. So continuity equation, I think, sir, it is, we can using the
It is a diffuser section. It is a diffuser section. If you are seeing something like a Mach number is supersonic here and subsonic here, just give me a second. Then so a normal shock wave should form inside this. So I think I just revealed the answer. You are able to now see this. A normal shock wave should form somewhere in the diffuser section. This is a normal shock wave. Is it clear?
Yes, sir, got it.
If you have a supersonic flow at the inlet, if you want to make the supersonic flow as a subsonic flow, you have to have a normal shock wave in the diffuser section. So that is the requirement. Not a requirement, but it is a common phenomena. Whenever a supersonic flow is entering into the diffuser section, the pressure difference is not sufficient. You will see because of the imbalance, there is a formation of normal shock wave, and you will see a subsonic pressure at the exit of the nozzle. And one more question I would like to frame is, if any subsonic flow or supersonic flow that is exiting to some particular pressure, that is back pressure PB or exit pressure, we can say anything, back pressure PB or exit pressure PE. Some cases those things will differ, but we are in general case and they are telling about. So whatever the fluid that is exiting from my nozzle, what is the pressure that is just coming out from the nozzle? Will it be the same as back pressure PB or PE, or will it be something else, or something else pressure depends on the stagnation pressure here at the inlet? You're like, are you clear? I'm just asking, what is the
Yes,
pressure
sir.
at the exit?
Sir, I think the pressure at the exit will be PB only, the back pressure. I don't know, sir.
Okay, the pressure at the exit. I'm just asking, whatever the fluid that is exit just coming out from the nozzle, will it be the same pressure at the atmosphere pressure or the exit pressure that we kept, the pressure difference that we kept? Suppose my pressure difference I kept as P naught at the inlet, I kept, and the PE at the exit, I kept as a PE as the exit. So this is the pressure difference I created. And if my flow that is exit, just at the exit of this nozzle, will it be having the same pressure at the PE, or will it be having something else? The something else means that depends on this flow velocity?
So something else only, sir.
Something else from this flow velocity. Okay. Any other answers?
Since it is jumping over a shock, so those normal shock equations, depending on the P naught stagnation pressure, it will be.
So your final conclusion is the same pressure or different pressure? Is it like
It will be different from the back pressure.
it will be different from the back pressure? So this is the common confusion people used to have is anytime, whether you are dealing with the supersonic flows or subsonic flows, all the time your back pressure, whatever the fluid that is just coming out from the nozzle, having the same pressure that exit pressure you kept. Some conditions that like where you are forming the under expanded, over expanded condition kind of situations are also there. We are not going to talk about those over expanded, under expanded conditions, but always, except those conditions, always the flow that is just coming out from this nozzle exit is having your back pressure, whatever the back pressure that you're keeping it. So I hope
So,
you're clear. Yes.
what is the reason of what is the reason behind it?
The reason is simple. Like if you are expanding any fluid to a particular pressure, you are creating the difference, right?
Yes, sir.
It is already making the difference from its velocity. Like if you are creating a pressure difference P naught and PE, the fluid that you are expanding it can only expand to the pressure that you kept outside, right? Is it
Yes, sir.
possible to expand more than that? I mean, still
No,
getting
no,
lesser pressure
no, sir.
or still having a more amount of pressure?
No, sir.
Not possible. But what is happening is it converts that energy into its kinetic energy and moves through the fluid and creates a low pressure again outside. I'm just talking about the outside. When it is coming with a high velocity here at the outside, it as it mixing it with the atmosphere, again the situations are different. But we are talking exactly at the exit. Okay. So at this exit, it is just expanding to the back pressure that you kept. Got it?
Yes, sir.
That's how the flow behaves. Then this is a small discussion on this. Let's go to the next question.
One minute, sir. What
Yes.
will happen if the shock is formed at the edge of the diffuser? Will it still remain the same, the pressure?
Exactly. The question is a good question. If you are having a shock exactly at the end, you will have the same PE. It is a good question that usually you will get in competitive kind of exams. They used to say that back pressure is this much and you have a shock here. Say just the shock is exactly at the nozzle exit or this diffuser exit. You will have the subsonic flow field, whatever it is generated here, that is marked less than 1, that will have the same back pressure you kept at the exit of the diffuser. So they won't give the pressure details here. They just frame that the question like the nozzle is not, the shock is at the exit of the nozzle. Okay.
Okay. Thank you.
So this it depends on how you are moving the shock. But whether shock is inside or anywhere, the moment that it is that you are considering the exit of the nozzle, the fluid always expands to the same pressure, uh, the back pressure you kept. So that is one thing. Let's go to the next question. Anyone, Ms. Kaumudi or sorry, Mrs. Kaumudi or Arihit, you just let me know whether this question is also repeated.
No, sir.
Okay. If this question is not repeated, let me
I
pause this.
think it is repeated.
Think it is repeated. The igloo. It's a very generalized problem. I hope you can recall it if it is repeated because there are some interesting landmarks are here. Canada, Central Arctic, Greenland, igloo. So these things you can maybe remember that. So assume you
Yes,
have
it is repeated.
it is repeated. Fine. So if it is repeated, also just whether you solved it or not, we can just see how we can solve this question today. So you have this igloo and you're sitting inside this igloo of 7-meter internal radius, hemispherical. It's not a complete spherical, it's a hemispherical. Which is having a 7-meter radius from the origin. And then, although outdoor temperatures are around 228.15 Kelvin, the inside temperature is maintained at 283.15 Kelvin when warmed by the body heat alone. There is no other heat source. It is the inside temperature is more only because of the body heat, no other temperature. And a inside pressure is also 1.01 times 10 to the power 5 pascals. Determine the internal energy and enthalpy, the room's air in megajoules. It's not asking only. We need the complete energy. We don't want in joules per kg Kelvin or something. We just need the complete energy present inside the room, both the internal energy and enthalpy. And we have some constants again here. So, like any idea how we can proceed for this? How to solve this question? Like we need to find the total energy present inside this igloo. That total energy means internal energy is one thing and enthalpy is another thing. So we need to calculate these two. The first formulation that we need to come into our mind is internal energy and enthalpy per unit mass is this one, CPT, and it's enthalpy, and this is for enthalpy and this is for internal energy. So these things we know, this is the basic thermodynamics. Now, how to get, the question is, we have the temperature inside and we don't have CP and CV. How to get CP and CV? But let's go in the step-by-step manner. Any idea of how to get the CP and CV?
We have
Sir, from our
gas constant and
Okay.
Yeah, please go.
One by one. Arhit, proceed.
Sir, from R we can find out CP and CV, and if gamma is given, we can find out from that to gamma and R we can find out CP and CV. Sir.
Can you state the relation?
Yes, CP by CV equal to gamma and CP minus CV equal to R.
CP by CP equals to gamma and CP minus CV equals to R. Okay. This is Kaumudi. Any further simplified of these equations?
same equations I mentioned.
Same equation. So these are the standard equations that we learned in any basic thermodynamics. But if you just substitute these equations in each other, you will get Cp is equals to gamma R by gamma minus 1. The direct formulation that we are writing. Instead of going details of it, you will get, you just need to substitute this as you have two equations, equation 1 and equation 2. If you substitute equation 1 and 2, you will end up with Cp equals to gamma R by gamma minus 1 and Cv is equals to R by gamma minus 1. So we have this constant and this constant and this constant, this constant. So all are known values here, and we will just only need to calculate the Cp and Cv. So if you do that, you will get, let me just write the answer instead of doing the mathematical calculations. What is the Cp and Cv you will get? You will get Cv is equals to 717.50 joule per kg Kelvin. This is the one you will get. This is a Cv value, and Cp is equals to, you will get 1004.50 joule per kg Kelvin. If you write it is in kilojoules per kg Kelvin, 0.717 joule per kg Kelvin. This is 1.004 joule per kg Kelvin. Is it 1.004? Okay, these are the miscalculation. Let me see. Okay, 1.004. This is the one. This is kilojoule, not a joule. So these are the standard values that we generally use for air. Even though if we don't have R and gamma, or if you have the R and gamma of the same values like 287 and 1.4, you will end up these values. You can also, I think it is very common that people used to remember these values while solving this kind of problems. So we now have CP and CV also. But the thing is, if you substitute this CP is equals to 0.717. Sorry, this is CV. I'm just substituting in this enthalpy equation. That is 1.004 times in kelvins we have. Yeah, inside temperature we have 283. 283 1 point. But if you see the okay, if you see the equation, we are just ending up with the kilojoules per kg. We still need to get what is the total mass of the fluid. Then only you will get kilojoules or whatever the units they require in megajoules. We can convert that, no issue. But now the question is how to get the mass, because we need to multiply this. This is H is the per unit mass. We need to find the total energy, that is H into the total mass present in the igloo. So this mass, how to get? Let me ask one by one. Arhit, you have any idea how to get this mass present in the igloo?
So that mass.
Yes, because now you have the enthalpy in kilojoules per kg. As you already multiplied with temperature, your temperature terms is gone. Now you have to find the mass in the igloo. How to find this mass in the igloo? Mass of the fluid inside the igloo. Because we see the units that we require is in megajoules, not megajoules or joules per kg. So we need to multiply the kg units is mass. It's referring to the mass. So we need to multiply with the total mass, then only we'll get the total energy. So
sir,
just think about it. Yeah. Yes.
Sir, is it from the pressure and that dimension of the igloo? We can find out mass. Just getting a
pressure, and can you frame that equation? How, like, dimension of the igloo is right, but what is the parameter that we need to find out first?
the P equal to P equal. In just a second, sir. I'm just thinking about it.
Okay. And other, Mrs.
Sir,
Kaumudi?
mass equal to
Yes.
Mass equal to density by volume, and
Okay.
sorry, density equal to mass by volume, and from that.
That's a nice approach. Okay, yes, that is the
density by volume, and from density we can. So we have that. We don't have the density, right, sir?
We don't have a density. Then how you can get the density?
From the ideal gas equation, I think.
Yes, sir.
Find
Yes, sir.
the density.
Yes, from the ideal gas equation. What is the ideal gas equation?
P is equal to
P-
rho RT.
Yes. Now P is equals to rho RT. We need to use the ideal gas equation. For this, we need to use the ideal gas equation. And why we need the rho? We need the rho to find out the mass, because we know the mass equals to density times volume. This V represents the volume. If you have the volume, you can multiply with the density to get the total mass. But how to get the density? It is C by RT. If you simplify this, P is equals to RT, you will get density equals to P by RT. So this density is just because you have the pressure 1.01 times 10 to the power 5 pascals by, and R 287 times, and the temperature 283 kelvins there we go. So you will get the density as, what is the density? Let me see. Yeah, the density inside this mass present, sorry, fluid matter present inside this igloo is 1.24 kg per meter cube. Now we have the density. We just need to multiply this density with the volume present here. What is the volume of this hemispherical?
2/3 pi r cube.
2/3 pi r cube for the sphere.
4/3 pi r cube.
Right. That's a simple geometry that you can use that. So now it is 2 by 3 pi r cube. We have r also that will give you the volume, and volume is 718.38 meter cube. Once you substitute this volume inside the here, then you will get the total mass equals to 890.79 kg, because you already have the density here. You just substitute this density and mass. So if you get those two, the idea is we already have the h per kg. H means small h we have, that is property, the total energy per kg. So just multiply this total mass, you will get capital H, that is total enthalpy. Total enthalpy is 253. It's a megajoules. We just need to convert the joules or whatever the number we get, a large number. We just need to get convert into the megajoules, that is N power 6. And enthalpy is this one, and internal energy, capital T, is 181 megajoules. Okay, so this is our enthalpy and internal energy in total. So that is a solution of this problem. So any questions,
Sir,
regarding this? Yes.
sir, can't we directly find this mass from PV equal to MRT?
V equals to MRT.
If
Which relation
R
you're
is
talking about?
the ideal gas relation, PV equal to MRT, but for
Oh,
that
you're
case,
yes, yes,
R
you
is
are
not
again.
specific.
Yeah, you are substituting again the same thing. This is PV is equals to rho RT. That is just P equals
Yes,
to
sir,
rho
from
RT.
that on.
Same thing that you are doing. We just
Yes, sir.
doing it, splitted it. You are just combining here. That PV equals to MRT. You are combining mass by volume. So that's it. Okay. So let's go to the next question. I think this is not a repetitive one. This is a repetitive one. Is it possible to recollect anyone?
No, sir, not repeated.
Okay.
Yeah, this is also repeated one is
Oh my. And all questions.
charging problem.
Okay. So let's have a short discussion on that. If that is the case, we can just have a look
sure,
on it, how to frame this question step by step. Now you have a pressure tank, high pressure storage tank, that you feeding the air into this high pressure storage tank. Let me draw the diagram of it. This is a generally image if you have any high pressure storage tank that we see. And if you have a compressor here, this is a compressor. And you are feeding to this, it has a volume of 103 meter cube, and you are feeding a mass at 5.5 kg per second is always entering into this chamber. And at this instant, the question is, at this instant, the reservoir it already has a pressure of, because you see the mass is always going inside this. From this question, what is the describing is mass that is 5.5 kg is always entering into this chamber. And since it is entering in the chamber and already there is certain amount of mass, because of that mass, you are having because of that result, you are having already an internal pressure of 15.15 10 to the power 5 Newton per meter square. This is distributed. It's assumed that it is equal everywhere in the pressure tank. So this much of pressure is already there inside. So during this charging procedure, this is instantaneous. That means at some particular time t, we are not dealing with the entire time. So at some particular time t, this is the pressure. And assume the heat exchanger keeps the air temperature inside the reservoir at 298.15. As you are compressing this air and increasing the pressure inside, since your pressure and temperature are interrelated, And also the amount of that you are compressing here fluid, it will also get heated up because the temperature raises because you are compressing it. And the same thing that is happening, temperature also raises here as you are compressing it. So the heat exchanger, some kind of heat exchanger is there. Like I will just, this heat exchanger is taking a heat continuously and maintaining the temperature always. It is static temperature that not depend on the time. So it is always able to maintain the temperature at 298.15 Kelvin. So these are the details given to us. And given another thing that's important thing, air is a perfect gas. We have air only. And the question is, the time rate of pressure increase in the reservoir at this instant. What is the time rate of increase in pressure? Let's see how we can approach this equation. We need only the time rate of increase in the pressure inside the cylinder. So again, we can start with any good idea what we can start? How we can start this question?
I think we can start with ideal gas equation and differentiate it with respect to time.
Yes, we can differentiate with respect to time. That is the usual process. And one more simplification is we no need to differentiate this here because you have the temperature inside is constant. The same thing that we will get again, the thing is, because if you see P is equals to RT, P is equals to rho RT, and here your temperature is constant and R is constant because temperature is keep on maintaining by the heat exchanger and R is a gas property that is not varying. The only thing that is varying is the mass inside this entire volume is varying and the fluid volume the volume you are keeping constant. So whatever the mass you are pumping into this pressure vessel is always increasing, but its volume is same. So your density is varying with time. So if density is varying with time, you will get the pressure is also varying with time. So we will get the particular uh, pressure, rate of change of pressure at that particular instant. Is it?
Yes.
So now our task is to find out what is the change in or rate of change of density. Arhit, are you here?
Yes, sir.
Okay. So are you able to understand this?
No, sir.
Where you missed it?
Sir, from the starting only I was.
So the question is, have you seen a cycle pump? Like when the compressor is running, you have a pressure gauge. Pressure gauge means something like this. It looks. It has the indicator. That dial indicator will increase. If you continuously run this compressor, the fluid enter into this same volume. Always the volume is same and you are pushing the mass into it and your compressor pressure, I mean, whatever the pressure inside this vessel will increase. Is it or not?
Yes, sir.
So as the pressure is increasing, will it increase at a constant rate or will it increase in a different rate,
In a,
like different rate
in a
means
constant.
because you are pumping with the mass with a constant rate, so the pressure inside also will increase the constant rate. By this ideal gas equation also we are able to tell that, but not directly we are telling it. So this pressure dial gauge is also moving it. So the question is, what is the rate of increase of pressure at this instant? How we can get that? If you see this equation very carefully, P is equals to rho RT. Your R is constant without, like, it is not varying with time. Your T is also constant because inside the temperature is maintained by some heat exchanger. I hope you know about this heat exchanger.
Yes, sir.
Yeah. So both are maintaining constant and your density is varying. You can you able to tell why your density is varying?
So due to the variation of mass.
Yeah, only mass is varying. You see, only the mass is varying at 5.5 kg per second inside the volume of 103 meter cube. So this is your um, like density rate of change of density. This you will get as 0.05 kg per meter cube second. So this is your density variation, the rate of change of density. So if you just substitute this rate of change of density in this equation, will you get a pressure at that particular instant or rate of change of pressure at that particular instant? What you will get?
Rate of change of pressure.
Rate of change of pressure at that particular instant. That is the end of the solution that you will get as rate of change of pressure is 4278.45 Newton per meter square. That's the simple. It's the question looks like lengthy and more conceptual. You have learned about heat exchanger, compressor, and everything in a real life kind of problem. And answer is simple that you are getting 4278.45. So hope you are clear now how to calculate this increase in pressure. Just 2 to 3
Yes, sir.
steps. Your question is right. Okay. So if no questions in this, no doubts in this, we can proceed for the next question. The next question also what we have, we need to use the same data and it's just a kind of velocity distance kind of problem, distance and speed kind of problem. Suppose the speed is the filling speed I can say, or increasing pressure increasing speed I can say. It just for your conceptual understanding, not for the detail. The speed that we derived in the last session, not in the last slide, is 45 times 10 to the power 5 Newton per meter square. Yeah, sorry, the speed we calculated in the last session is this one, 4278.45 Newton per meter square per second. This is the speed at which your pressure is changing. I should not use the term speed, but this is the rate at which your pressure is changing. If something is changing with time, we generally indicate with a dot, P dot. We say it as a P dot. That is, P is not a constant, it is changing with time. So how it is changing? It is changing with 4278.45 Newton per meter square second. So if that is the case, and your P1 temperature P1 is 15.15 times 10 to the power 5 Newton per meter square, and your P2 is 45 times 10 to the power 5 Newton per meter square. And they're asking the time delta T equals to question, and you have the rate of difference, that is P2 minus P1 by delta T equals to P dot is equals to 4278.45. Okay, so this is the details you have. The rate of change of pressure with respect to time is this one. We already just obtained from the last slide. The same question is continuing. So they're asking is how much time you require to change the pressure from, like, you to increase the compression, the pressure in the tank, the pressure high pressure storage tank. If it is now at 15 pascals or 15.15 something, at 15 pascals, if you want to increase it to 45 pascals, how much time it needs? It is again simple, like pressure distance kind of formulation. If it is velocity, if you consider this, you are just writing it as T2 minus T1 by change in time, and you are using the corresponding value. If you calculate, just substitute these values, you will get delta T equals to 11.63 minutes. In terms of minutes they ask, so you will get the solution as 11.63 minutes. I think this is clear for you. It's a very simple
Yes,
problem.
sir.
Yeah, no, I think no need to explain it again. So that is the one thing. And let's have this last question for today's discussion. This question is, which option for the following statements is correct? That is, finite waves intersect at infinity and finite compression waves intersect at finite distance. Finite expansion waves, we know that at compression, this is kind of corner, expansion corner, we will have the expansion waves like this. Okay, so in this expansion waves, we won't see any intersection of this expansion waves, even if you travel with at infinity speed, like not infinity speed, at infinity time also, you won't see any intersection. And finite compression waves like this, if the finite compression waves are forming like this, you will see something this kind of phenomena. The theory is here, if you have any drastic change, because every finite wave is able to create some particular difference of the property. Like if you have any finite wave like this, it can create a delta rho or delta t or delta p. It will create a change in finite amount of or significant amount of change in property. If these things are intersecting at a particular point or a particular line, if these are all intersecting, that means coming to only one line, it is not physically reasonable, because everything should every finite wave should able to create some particular difference in the property, and these are merging at single instance, that leads to a violation of your second law of thermodynamics, because it as individually should do. That means all these waves should should not intersect, but merge like very thin kind of layer. That is what we are shock layer. It is not intersecting, but those are merging like very small thin layer. So all these things are framed by one by one, and they looks like very thin kind of layer, and but those are not overlapping on each other. So the both the statements are false here. So that is what a common idea of, like we always this question frame, because we always misconception having of these compression waves intersect on each other, but they just overlap on each, not overlap, uh, creates a thin layer of the shock wave, as the number of these compression waves are are coinciding at this particular point. So they are just a merging, but not overlapping on each other, because every finite wave has a property or changes. It creates some changes in the fluid property. Okay. Yes.
Yes, sir.
So that's end of the today's discussion. Let me
Sir,
stop
I got
sharing my.
sir, I
Yes,
got this
we have.
option. I got this question wrong, sir, in the assignment.
Okay.
I
Okay.
thought that, sir, it really intersects, and after the solution came, then I
Yeah,
could
that is the
understand.
reason why they pose this kind of question.
Yes, sir.
So I just stopped sharing my screen. Let me stop recording this.